In Volume 1 of TCCS Part 2, we studied these items. In this volume, using a 4A GE engine mounted on the 1986 Celica as an example, we will learn about inspection of the following circuits. The throttle position signal circuitry and idle signal circuitry, the intake manifold pressure signal circuitry, the ignition signal circuitry, and the water temperature signal circuitry. Problems in these signal circuits can be detected by the diagnostic function. Now we'll see how the throttle position signal circuitry and idle signal circuitry are inspected. If there is an open or short circuit in the throttle position signal circuit, the check engine lamp indicates diagnostic code number 7. The throttle position sensor is installed onto the throttle body. The throttle position sensor detects engine idling and the throttle opening angle as a change in voltage. This is a cutaway model of the throttle position sensor. This is the idle contact point. When the accelerator pedal is depressed, the idle contact opens. As the throttle valve opens further, the movable contact slides over a resistor. Now, let's look at the electronic circuitry of the throttle position signal. Five volts are applied by the ECU to both ends of resistor R within the sensor. And movable contact point A moves along the resistor as the throttle opening angle changes. The potential at terminal VTA of the ECU therefore varies accordingly. Let's inspect the circuitry now. First, measure the voltage between terminals VCC and E2 of the sensor connector with the connector connected to see if the standard voltage is being applied to the throttle position sensor. Now, let's see how to actually check it. If the measured voltage is equal to the standard value, we can say that the constant power supply circuit of the ECU is normal. However, if the voltage reading is 0, what should we check? In this case, there are several possible causes. A short circuit between VCC and E2 in the sensor. An open in the wire harness. A short circuit between the wiring and grounding. Or a defective ECU. To locate the problem, measure the voltage at the same terminal with the connector disconnected. Let's see how to actually check it. If the measured voltage is equal to the standard voltage, you may have to replace the throttle position sensor. If the voltage reading is still 0, we have to check further. To determine whether the problem is in the wire harness or in the ECU, first, measure the voltage between terminals VCC and E2 of the ECU connector. Let's actually check it. If the measured voltage is equal to the standard value, there may be an open in the wire harness. If no voltage is found, there may be a short circuit in the wire harness. Or the ECU itself or its grounding could be at fault. Now, let's see how to inspect further when the voltage that is being applied to terminal VCC of the throttle position sensor is the standard voltage. The next check we should make is a measurement of the voltage between terminals VTA and E2 of the sensor connector. Now, let's see how to actually check it. If the voltage at VTA changes smoothly within the specified range in accordance with the throttle opening, we can conclude that the throttle position sensor is operating normally. But if the voltage does not increase in proportion to the throttle valve opening angle, or if it does not increase continuously and smoothly, what could be the cause? We may conclude that the movable contact of the throttle position sensor is making improper contact, or that the sensor connector is in poor contact with the wire harness connector. If the measured voltage remains at about 5 volts, there may be an open between A and E2 in the sensor, or a short circuit between VCC and VTA. If the voltage at terminal VTA of the sensor changes smoothly, we should check the change in the voltage at terminal VTA of the ECU's connector in the same manner as we did before. Let's check it now. If the voltage does not change in this test, what should we check? Yes, we need to check the wire harness between the throttle position sensor and the ECU. Now, we will disconnect the terminal of the VTA signal wiring to see what will happen. Using the service wires, we try it. It does not seem to make much difference, does it? This is because of the fail-safe function, which causes the ECU to control the system as if the throttle opening angle were 25 degrees, regardless of the actual angle. Now, let's check the idle or IDL signal. When the throttle valve is fully closed, the IDL contact is closed. So the voltage at the IDL terminal of the ECU is 0. When the IDL contact is open, on the other hand, about 5 volts are measured at IDL terminal of the ECU. Now let's actually check it. If the voltage between terminals IDL and E2 is 0 when the throttle valve is fully closed, and 5 volts when the throttle valve is slightly open, the IDL signal circuitry is okay. Now, we will show you another method for checking the IDL signal circuit using the diagnostic function. Turn the ignition switch on, then connect terminals T and E1 of the check connector using a service wire. Read the diagnostic code with throttle valve fully closed. Yes, a normal code is being output. Now, depress the accelerator pedal slightly and see whether diagnostic code number 11 is being output. If it is, it means that the IDL signal is being correctly input into the ECU only when the throttle valve is closed. Now, let's ground the IDL terminal and see what will happen. Yes, this represents a condition in which the IDL contact remains closed. Let's actually short-circuit terminals IDL and E2 of the ECU to simulate that condition. The engine seems to be idling normally. What will happen when we increase the engine speed? Yes, the engine starts hunting. This is because the ECU cuts off the injection of fuel when the engine is running above a certain speed with the throttle valve closed. And resumes the fuel injection when engine speed drops below a certain speed. Hunting is the repetition of this process. Now we'll look at how to check the intake manifold pressure signal circuitry. If the the check engine lamp indicates a diagnostic code 2, there is an open or short circuit in the intake manifold pressure signal circuitry, or PIM signal circuitry. Before checking the PIM signal circuitry, let's review its operation. This is the vacuum sensor. And this is a cutaway model of it. A silicon chip is installed inside the vacuum chamber, and manifold pressure acts on this chip. This is a hybrid IC, or integrated circuit. Let's study the circuit diagram of the vacuum sensor. The VCC terminal of the vacuum sensor receives 5 volts from the constant power supply circuit of the ECU. The electrical resistance of the silicon chip changes in accordance with the pressure that acts on the chip, and therefore with changes in the manifold pressure. These changes in resistance are converted into changes in voltage, and then amplified by the hybrid IC. This voltage signal is sent to the terminal PIM of the ECU. If we consider the silicon chip and hybrid IC in the vacuum sensor to be a variable resistor, the PIM circuitry is basically the same as the electrical circuitry of the throttle position signal, or VTA circuitry, that we studied previously. Therefore, the PIM signal circuitry can be checked in basically the same way as the VTA circuitry. Now, let's see how to inspect further. When the ECU is outputting the standard voltage to the VCC terminal of the vacuum sensor. The next check we should do is to measure the voltage at terminal PIM of the ECU. Let's see how this check is made. First, connect a multivac to the vacuum sensor, like this. Then, measure the voltage between terminals PIM and E2 of the ECU under ambient atmospheric pressure and record it. Now, using the multivac, apply vacuum to the vacuum sensor in steps of 100 millimeters of mercury until 500 millimeters of mercury is reached, and measure the voltage drop for each step. The vacuum sensor is in good condition if the voltage changes and matches the specified value every time vacuum is applied during the test. If the voltage at terminal PIM does not change, check the wiring between the sensor and the ECU. If the wiring is in good condition, there may be a problem in the vacuum sensor. What will happen if PIM signals from the vacuum sensor are not actually received by the ECU? Let's disconnect terminal PIM of the vacuum sensor connector and see what will happen. Well, what do you know? The engine started anyway. This shows that although signals from the vacuum sensor are essential in determining the basic fuel injection duration, as you may recall, the engine can actually run without the ECU receiving this signal. How is this possible? The engine is running at an idle speed, although roughly. Let's increase the speed a little. The engine is still running. Why is that? That's right. The engine is running without the PIM signal from the vacuum sensor because it is running under the control of the backup mode. Now, let's look at the injection signal on the oscilloscope. This shows the injection signal in normal engine operation. The injection duration varies as the engine speed changes, as you can see here. Now, we disconnect the PIM terminal of the vacuum sensor connector. The engine is running in backup mode. The fuel injection duration is fixed at a constant rate. The amount of injection is not the only item that is fixed in the backup mode. Do you remember the other? Yes, we learned that the ignition timing is also fixed in the backup mode. Let's see if this is really so. In normal engine operation, the ignition timing will change as the engine speed changes, like this. Now, let's disconnect the PIM terminal of the vacuum sensor connector. The ignition timing remains near 10 degrees before top dead center, even if the engine speed changes, as you see here. Now, we'll see how to check the ignition signal circuitry. If no ignition confirmation, or IGF signal, is being input to the ECU, the diagnostic function detects this and outputs the diagnostic code number 3. Before we start checking, let's briefly review the operation of the ignition, or IGT signal, and IGF signal circuitry. The ECU outputs voltage to terminal IGF of the igniter. However, the IGF terminal of the igniter is normally grounded via the transistor A when the ignition switch is on. Just before the crankshaft reaches the angle at which ignition is to take place, the ECU sends IGT signal to the igniter. Based on this signal, the igniter actuates its power transistor B, causing the current to flow in the primary coil. When the crankshaft rotates to the ignition angle, the ECU stops sending the IGT signal to the igniter. This causes the power transistor B to turn off, halting the flow of current to the primary coil. This in turn generates high voltage in the secondary coil, causing the spark plugs to fire. After ignition has taken place, counter-electromotive force generated in the primary coil causes transistor A to turn off. The voltage at terminal IGF of the ECU therefore becomes 5 volts, informing the ECU that ignition has actually taken place. Now, let's see how to inspect the IGT and IGF signal circuitry. First, perform a spark test to see whether the trouble is located in the IGT or the IGF signal circuitry. Let's see how this is done. If no spark is produced in this test, we can conclude that there may be a problem in the IGT signal circuitry. However, before checking the IGT signal circuitry, what should we check? Yes, we have to check the supply of power to the igniter and the ignition coil. First, disconnect the connector of the igniter. Then, measure the voltage between terminal plus B and body grounding with the ignition switch on. Let's see how to actually check this. If there is no voltage at terminal plus B of the igniter, check the wire harness between the ignition switch and the igniter connector. If there is a voltage at terminal plus B, reconnect the igniter connector, then check the supply of power to the ignition coil. Let's see how to check the supply of power to the ignition coil. If no voltage is applied, check the wiring between the igniter and ignition coil to see if there is an open in the wire harness. If the wiring is okay, the problem may be in the igniter. If voltage is being applied to the positive terminal of the ignition coil, next, check the resistance of the ignition coil. This shows how to check the resistance of the primary coil. And this shows how to check the resistance of the secondary coil. If no problem is found during all the checks we have done so far, measure the voltage between terminals IGT and E1 of the ECU during engine cranking to see if the ECU is outputting the IGT signal. If the measured voltage is within the standard, the ECU is outputting the IGT signal. Therefore, the trouble may be in the wire harness between the ECU connector and igniter connector. If the wiring is okay, there may be a problem in the igniter. If the engine won't start, even if a spark is produced in the spark test, we have to check the IGF signal circuitry. First, disconnect the connector of the igniter, Then measure the voltage between terminals IGF and E1 of the ECU with the ignition switch on to see if the ECU is outputting 5 volts to the IGF terminal of the igniter. If there is no voltage at terminal IGF, it may be due to a faulty ECU. If 5 volts are found at terminal IGF, connect the connector and measure the voltage between terminals IGF and E1 of the ECU with the engine cranking. Now let's see how to check the IGF signal circuitry. First, disconnect the igniter connector. Then, measure the voltage between terminals IGF and E1 of the ECU with the ignition switch on. If 5 volts are measured, connect the igniter connector. Then, measure the voltage between terminals IGF and E1 of the ECU while the engine is cranking. If the measured voltage is within standard, the IGF circuitry is okay. However, if 5 volts are being applied to the IGF terminal, there may be an open in the IGF wiring. If there is no voltage at terminal IGF, it may be because there is a short circuit between the IGF wiring and body grounding. If there is no problem in the wiring, the igniter may be defective. Now, let's see what happens when an open develops in IGT or IGF signal circuits. First, we disconnect the service wire connector of the IGT signal wiring and crank the engine. Naturally, the engine won't start because ignition will not occur. Next, we will reconnect the IGT terminal, then disconnect IGF terminal. Now, ignition does occur, but an IGF signal is not returned to the ECU. Therefore, the ECU stops the injection of fuel and the engine will not start. Finally, let's see how to check the water temperature signal circuitry. If the check engine lamp indicates diagnostic code number 4, it tells us that there may be an open or short circuit in the water temperature signal circuitry. This is a water temperature sensor and contains a thermistor. Let's look at a circuit diagram of it. The ECU outputs 5 volts to terminal THW of the water temperature sensor. Since the resistance of the thermistor changes in accordance with the coolant temperature, the voltage at terminal THW of the ECU changes accordingly, informing the ECU of the coolant temperature. Let's start inspection of this circuit by checking the water temperature sensor itself. First, disconnect the connector of the sensor, then measure its resistance. If the measured resistance is within the standard range shown on the chart, the water temperature sensor is okay. If the sensor is okay, connect the connector. Then, measure the voltage between terminals THW and E2 of the ECU with the ignition switch on. If the voltage reading is neither 0 nor 5 volts, the water temperature signal circuitry is functioning normally. However, if no voltage is found at terminal THW, there may be a short circuit in the wiring. Or it could be due to a defective ECU. If the measured voltage is about 5 volts, there may be an open in the wiring. Or the E1 terminal of the ECU is not grounded properly. Finally, we disconnect the connector of the water temperature sensor to see what will happen. Let's disconnect the connector at the sensor side and start the engine. For your information, the coolant temperature reading is 5 degrees centigrade at this moment. What could be causing this hunting? We can understand this by looking at this chart, which shows the fuel injection cutoff speed and resumption speed while the engine is cold and after it has warmed up. The circles colored in yellow show the actual idling speed of the engine at these times. As you can see here, the fuel injection cutoff speed is higher when the engine is cold than when it is warm, because the engine is running at fast idle. If there is an open circuit or a short circuit in the water temperature signal system, the ECU controls the system as if the coolant temperature were 80 degrees centigrade, that is, hot, regardless of the actual temperature. So, the ECU will cut off fuel injection when the engine is running at fast idle. This is why hunting occurs. In part 2 of this video presentation on the TCCS, we have looked at how to inspect the main signal circuitry of the TCCS. The other circuitry can be inspected in basically the same way.